This video is about equations and inequalities involving absolute value. To begin this topic, we're just going to think for a second, just to get warmed up here. If I had the expression absolute value of x equals 6, and then I wanted to think through what this would actually mean. Let's do so by first kind of imagining that this x inside of the absolute value was covered in a curtain. So we're going to just disguise what's inside that curtain, inside the absolute value. But think of this. If I have the absolute value of whatever that is equal to 6, given what we know about absolute value, that really would give us two options for what's inside the curtain. Really, it could be that value of x as positive 6 because the absolute value of 6 is 6, or it could be x equal to negative 6 because the absolute value of negative 6 equals 6 as well. So that's just kind of depending on or using or recalling what we already know of what absolute value means. But we're going to use that simple understanding to be able to solve equations that involve these absolute value expressions. So let's do some examples where we want to solve. The first example has the absolute value of, and then x plus 1 is inside it, and that's equal to 5. Now, with simple enough examples like this, it's sometimes true that, students can look at it and just kind of figure it out by doing maybe a little guess and check or just thinking about it for a second. But I'd like us to try to apply what we observed in the very simple example above, in that we could imagine that what is inside this absolute value could be two different things, right? I'm not going to draw the curtain over it this time, but you could, if it helps to visualize it. What's inside the absolute value, which is the x plus 1, could be equal to a positive 5, or that x plus 1 could be equal to a negative 5, given that the x plus 1 is what's inside the absolute value, and we know that that is what will turn into a positive 5 result if we use the absolute value on it. Now, given that those two different options could be what's inside the absolute value, we can simply rewrite two simpler looking equations. So x plus 1 equals 5, or x plus 1 equals negative 5. Of course, the x plus 1 is what's inside the absolute value at the beginning here. But that gives us two much simpler equations to solve, and we should solve both of them. So if we simply subtract 1 from both sides in the left version of this, we'll have x equals 4. Or on the right side, same thing, subtract 1 from both sides. That would give us x equals negative 6. Turns out both of those are valid answers or solutions to this equation, because if you plugged either one of them in for x, this equation would indeed be true, even though it has this absolute value. So this idea of splitting an absolute value expression, which is involved in an equation like this, into these two options where what's inside the absolute value is equal to either the positive or the negative version of what's on the other side of the equation, is a nice way to handle this in a more simple understanding. So these would be two solutions. You could see them expressed just as we have them here, boxed in, or sometimes you may see, some authors will write out a solution set, and if it has multiple answers, you would put them in set notation as 4 and negative 6 separated by a comma. You could see an answer written that way or a solution written that way as well. Our second example begins as 3 times an absolute value expression, where inside that absolute value we find y plus 5. So the 3 is out in front being multiplied with this absolute value expression. And then that's equal to 12. Now what we just saw with this little strategy of splitting up the absolute value works great unless there's other factors or terms surrounding it. So this 3 that we find in front, we actually don't want there in order to be able to split this one, which means what we can do is, since that 3 is simply being multiplied with the absolute value expression, we can divide by 3 on both sides, because then the 3's would cancel on the left side, leaving us with absolute value of y plus 5 equals, on the right side, 12 over 3 is 4. And this takes us to a much simpler version like we saw in the previous problem, where we can now split this as y plus 5, that's what's inside the absolute value, equals positive 4, the value on the opposite side, or y plus 5, what's inside the absolute value, equals negative 4. In each case, it's a much simpler linear equation where we can subtract 5 from both sides, which will yield, in the first option on the left side here that we wrote out, y equals negative 1, or, in the other case, when we subtract 5 from both sides, y equals negative 9. So both are valid solutions to this equation. Let's consider a third example. This one begins as the absolute value of, inside it we have 3y minus 2, and then we say plus 8 equals 1. So, okay, kind of like we just mentioned in the previous example, we want to do the splitting, but we really can't split up the absolute value expression until we get it alone. So we're going to start by subtracting 8 from both sides, which would be a way to get the absolute value alone. And if I do that and rewrite, I'll have the absolute value of 3y minus 2 equals, and then on the right side I have 1 minus 8, which is just negative 7. Now, at this point, you could try to go through the splitting process like we've done above. However, we also want to catch something important right here, which is this would never actually happen. So I'll put here a note, cannot happen. And the reason it cannot happen is because we have an absolute value expression equal to something negative. But remember, the definition of absolute value is that it will turn whatever's inside of it into something positive, whether it starts positive or negative inside of it. And so it will never be equal to a negative 7, like this one is supposing. Since that is the case, we don't have to go through any splitting or anything else. We would just say there's actually no solution to this equation, so we can just use the symbol for no solution or write it out, but there's no way that this could happen, so no solution is our answer. Let's try yet another example. This one begins as the absolute value of, and then inside of it we have 3x minus 2, close absolute value, and then after that we have plus 4, and then equals 4. So we'll go through the same kind of process here where we want to isolate or get alone the absolute value expression first. And we can do that by simply subtracting 4 from both sides. That would eliminate that plus 4 that was next to it, which leaves us with the absolute value of 3x minus 2 equals, and then on the right side we have 4 minus 4, which is just 0. Now, in the previous example, we said there was no solution because the absolute value could not equal something negative, and that's true. But in this case, we have the absolute value equal to 0. That's actually okay. But notice what happens here. If I were to try to split this one, it would become trivial. I would have 3x minus 2 equals 0, or 3x minus 2 equals 0. There's no way to say positive 0 and negative 0. 0 is not positive nor negative. So we wouldn't actually need to write out both of those versions. One of them would give us the solution, which means if I add 2 to both sides, I would have 3x equals 2, divide by 3 on both sides, and I'll have x equals 2/3. And that is the one singular solution to this equation, since both branches that we would normally have found really are the same. We just have one solution. Let's try another example that is slightly different. This example begins as the absolute value of, and then inside it we have 4x minus 9, and that's equal to the absolute value of 2x plus 1. So notice the difference here is that we start with an absolute value on both sides of the equation. In the previous examples, we only had an absolute value on one side, and then just a number on the other side. Well, in this case, when you have an absolute value on both sides, you could actually treat it very similarly to how we've been doing those above, which is we're going to split this, And just to keep things simple, though there actually is a little variety in how you can set up the split here, I'm going to suggest we do it just like we've been, which is I'm going to keep the left side expression that was in the left side of this equation in the absolute value, that is the 4x minus 9. I'm going to copy that one down to be the same in both cases. So I have 4x minus 9 equals and 4x minus 9 equals. Kind of like we were doing above, right? In the ones above where we actually had to split them, we kept what was inside the absolute value as the same in both sides of the equation. Like if you go way back up to number 2, there was a y plus 5 and a y plus 5 that came from the y plus 5 inside that absolute value. Well, if you kind of apply that same pattern or visual thinking to this example, that's exactly what we just did. We took the left side inside the absolute value, the 4x minus 9, and we copied that down as it is, exact same thing in both cases. Then on the right side, we're simply going to put the positive version of the right side absolute value expression. So in that case, 2x plus 1, that's the positive version of it, or the negative version of it, which I'm going to write as negative and then in parentheses 2x plus 1. So that's kind of following the exact same pattern we did above, where you have the positive and negative version of what was on the right side. But I like to put the parentheses for the negative version with the negative out in front of it, because we're going to have to distribute that negative in a second, and it's easy to forget that if you don't use the parentheses. Of course, you could also just distribute it as you write it and put negative 2x minus 1, but even that gets easy to forget sometimes. So let's go ahead and do it this way, just a suggestion where we copy down the left side expression as is, and then the right side is the one that's now positive and negative. I will also say it's possible to make one common mistake, which is sometimes students in learning this little patterned visual process of splitting things up will often think, oh, I should make one of these signs between the 4x minus 9 positive and one of them negative. That's actually not how we're doing this. The positive and negative alteration that's happening is simply on the right side, not the left side, the way we've split them. So just be careful of those common ways to get turned around in these. Once we do the splitting with the positive negative, we simply solve these simpler equations, and so we'll go ahead and subtract 2x from both sides. I'm working on the left side one here first. That would give us a 2x minus 9 equals 1. Of course, you could add 9 to both sides now and get 2x equals 10, in which case x would equal 5. That's one of our solutions. On the other side, we would now have to distribute this negative sign, as I mentioned before. So we have 4x minus 9 equals negative 2x minus 1. Then we solve like usual. We could add 2x to both sides and get 6x minus 9 equals negative 1. And then add 9 to both sides to get 6x equals a positive 8. And then we'll divide by 6 on both sides to get x equals 8 over 6, which of course you could reduce. So let's go ahead and just write this out as our other solution here. X would equal 4/3, which is just 8/6 reduced. So we have two possible solutions here, the x equals 5 and the x equals 4/3. Now moving on, still within this topic, we're going to discuss absolute value inequalities. So we just got done discussing and doing examples of absolute value equations, but the reason I like to bundle it directly with the inequalities is because I prefer this method that's out there that I think works really well, not only for these, but later topics as well that we'll be discussing, and it's called the SPIT method. Now, SPIT's an acronym, S-P-I-T, and the S stands for solve, P stands for plot, I stands for interval, and T stands for test, or you could say IT is interval test. So this method is a way to stay organized and get through these problems and many others, and I like the kind of thinking that it includes, so I'm going to suggest we use it for these absolute value inequalities. It's not used for the equations, but as you'll see very soon, it actually borrows what we just discussed in the equation scenario. So let's go ahead and try some examples. Now for these, the instructions will say typically something like solve, graph, and then write using interval notation. We've actually done those exact steps when discussing inequalities before, So we're doing them again here, but now the inequalities involve absolute value expressions. Our first example is the absolute value of x minus 2. So the x minus 2 is inside the absolute value symbols, and that is greater than 5. Now, to demonstrate this solve, graph, and write using interval notation using the SPIT method, the first thing we do is actually change the problem. So we're going to copy down or rewrite the exact same problem, except I'm going to change the inequality to an equal sign, okay, which is not okay unless we put it back by the end. So this entire SPIT process will account for this being okay, but it's not okay just to do this in general. I want to make sure that's clear. But in the SPIT process, we're going to solve it as if it's an equation. So I'm going to now turn it to an equation. The way this fits in is that we just solved these kinds of equations. Remember above? This is where we split an absolute value equation into two options. So what's inside the absolute value here, the x minus 2, will be equal to the positive number 5, or we'll have x minus 2 equal to negative 5. Just like we did above with the absolute value equations. Now we'll solve each of these. If I add 2 to both sides, I'll get x equals 7. Or if I add 2 to both sides in the other equation, I'll have x equals negative 3. So that is the step known as solve. In the SPIT process, we just got two solutions to the equation version of our original inequality. So we changed it to an equation and solved it using what we know already about absolute value equations. Then, okay, we're not done. That was just the solve step. Next, as you'll recall, is the plot step. For SPIT, SP, P is plot. So what we're going to do is draw out a number line, and we're simply going to plot our solutions on it in relative order. So I have negative 3 and 7 as my solutions. Negative 3 would be somewhere to the left, 7 would be somewhere to the right, but we don't really need anything else on the number line, just those solutions plotted. Okay, that's the plot step. So let's go ahead and mark this out. That's plot. And of course, the last step is called interval test. I'll just go ahead and write that out now. Interval test, because that's our last step. Okay, for that step, what we're going to do is go to our plotted number line, and we're going to pick on some values that would represent the intervals. Notice putting two values on our number line creates three different intervals. It's basically left, middle, and right surrounding those two solutions. What we want to do is test values that are representing each solution, which, by the way, could be any number in those intervals. So I want to test something to the left of negative 3, and I can pick any number to the left of negative 3, so don't make your life miserable. Pick something simple, like how about negative 4? Okay, so we're going to test negative 4, and by the way, we test it by plugging it into the original inequality. So, and for x at that. So I'm going to write out absolute value of x minus 2, but instead of x, I'm going to put a negative 4, okay, and then minus 2. That's inside the absolute value, and I have that greater than 5, or supposedly it is. We don't know yet. We're testing it. This is how we're plugging the test values back into the original inequality. We simply want to know, is that true or false? Well, doing the simple arithmetic involved would mean we have absolute value of negative 6. We're still wondering, is that greater than 5? Well, the absolute value of 6 is 6, and therefore, yes, 6 is greater than 5, which means that's true. So what we're going to go do is mark that interval as true by putting a capital T in its place. This is just one way to stay organized with it. But that was only one interval. So now we're going to move on to the next. I'll use a different color for the next one. In that next interval, we have to pick some value to represent it, which could be any number in between negative 3 and 7. Well, that range happens to include my favorite number, 0. So to test 0, we're going to do the exact same thing by plugging it into the original inequality for x. So if I have x minus 2, I'll plug in 0 for x and get 0 minus 2 inside the absolute values. And I have that possibly greater than 5. We don't know yet, that's why we're testing. this would result in 2 greater than 5, which of course is not true. So we're going to mark that false, which means we go back up to that middle interval and put a capital F above it since it's false. And that takes care of those two intervals. Now we'll do the exact same thing in the right side interval. So let's pick yet a different color. And to the right of 7, we need to test any number to the right of it. Again, don't make your life harder than it has to be here. Why don't we just pick 8? It's clearly to the right, and it's not too far, not too crazy. So if we plug 8 in for our test value, that's testing the absolute value of 8 minus 2. We're plugging 8 in for x in the original. We're wondering, is that greater than 5? Well, 8 minus 2 happens to be 6, and the absolute value of 6 is 6. So is 6 greater than 5? Yes, actually it is. So we'll call that true, which means we can go back up and label that interval to be true as well. Okay, now I know what you're thinking. This is a ridiculous amount of work. In some ways, yes. It seems like more. If you go back and find another way that a textbook may instruct on this topic of absolute value inequalities, you will see a lot less writing typically, because the usual way it's discussed in a textbook is not this extensive. However, the usual way discussed in a textbook is often misunderstood and usually therefore incorrect. So I highly suggest the SPIT method. Plus, all this work, if you get this down now, will be reused in later topics when we do more complicated looking algebraic inequalities. So these are just absolute values. There are other nonlinear inequalities that can be solved the exact same way using the SPIT process. So it's worth your time to get this down now. Of course, we're not quite done. Let's go ahead and finish the question, which said to solve, graph, and write using interval notation. Well, we actually have the solution in disguise right in front of us. So let me go ahead and take our number line and just kind of pull down our solution, which we translated in the following way. We only graph where it's true. So look at our graph. We have two places it's true. That's to the left of -3 and to the right of 7. So that means for our solution, we're going to draw a number line, put the exact same boundary values on it, so -3 and +7, but then only graph where it's true. So to the left of 3, we'll have an arrow going left, and to the right of 7, we'll have an arrow going to the right. That represents only the places where it was true. In between these two values, in the middle, it was false, so we just don't graph anything there. Then we go back up to the original inequality to get the boundary symbol. This was a strict greater than, which as you know corresponds to parentheses. So we'll go ahead with our graph and just mark those two arrows. So to the left of -3, there's a parenthesis opening that way. To the right of 7, parenthesis opening that way. That's our graph. And then of course the interval notation will be the summary of these. So we have -infinity as the left boundary with that left arrow, comma, -3 with a parenthesis. But then we have this space in between that's not included, but we want to include the right side as well, so we're going to union these together with a big union symbol, which looks like a capital U in some sense. And then after that union symbol, we'll put a parenthesis with 7, comma, +infinity, representing the right side interval. So it's like two intervals glued together with this union symbol, and this will represent the entire solution to this original absolute value inequality. So again, you may not like how much this involves at first, but I guarantee in the long run it's going to pay off, and I highly suggest using this method if you want to get these correct. Let's try another example. This one begins as -2 out in front of an absolute value expression which contains 5 minus x inside of it. So it's -2, absolute value of 5 minus x, close the absolute value, then this is less than or equal to -6. Now, as we saw actually back up in the equation absolute value examples above, it's actually best to get the absolute value eventually alone. We want to go ahead and try the SPIT process on this one as well, which as we noted above would involve recopying the problem, except changing it from an inequality to an equal sign, which remember is not okay unless you do the rest of the SPIT process. So I'm going to rewrite this out as -2, absolute value of 5 minus x, close absolute value, equals -6. Now, with this being an equation, it operates just like the ones we did way above, which is we'd like to isolate or get alone this absolute value before we split it. So let's go ahead and divide both sides by -2 in order to do this. On the left side, these 2's will cancel, the -2's, sorry, leaving us simply with a absolute value of 5 minus x. Over there on the right side, we have -6 over -2, which is a +3. So we'll continue to solve this using what we had above about absolute value equations, which is to split it up. And this time we'll be writing 5 minus x, that's what's inside the absolute value, equals +3, or a 5 minus x equals -3. So we're going to go through and solve this. Now I must say, just because I'm sure someone will wonder, can't I get rid of the -2 right away by dividing both sides by -2, even in the inequality form? Or should I do that, or should I not do that? You actually could do that, and that would involve, though, dividing by -2, which would involve changing the direction of the inequality. It'll work out, or it should work out, so that's also a valid option. But let's go ahead and keep going this way that we've already kind of taken at this point and finish it. So we're still working on the solve step where we've turned this into an equation. Now we're solving the absolute value equation using everything we know about that. That would involve, with the 5 minus x equals 3, if I were to get x alone on that one, I would get x equals 2. That's one of our solutions. On the other side, I have 5 minus x equals -3. If I were to get x alone there, I'd end up with x equals 8. Okay, I'm just maybe not writing out a couple steps there, but ultimately that's how we could solve those. Now, if those are two solutions, remember the split process involves not only solve, but then plot. So let's go ahead and plot them on a number line in order. So we'll have a 2, and then somewhere to the right of it an 8. And that's the plot step. The next step would be to interval test this. So let's test the following. To the left of 2, remember you could pick anything. You could pick 1, you could pick 0. I like 0. Let's pick that, it's easy to test. We'll test 0. Of course, to test it, we're plugging it in the original. Now, if you go all the way back to the original, because we left it without dividing by the -2 right away, it's a little bit more to plug in and test, but it works just fine. So let's go ahead and do it by plugging in 0. We'd end up with -2, absolute value 5 minus 0, close absolute value less than or equal to -6. So that's literally the original problem, but now just plugging in 0 for it. We just have to know, is this true or not? Well, there's a little bit of arithmetic involved in this, and you should end up finding that this is indeed true. Remember, this 5 minus 0 is 5, the absolute value of 5 is 5, -2 times 5 is -10, which is certainly less than -6. Okay, so I just kind of blew through that arithmetic there, but that's all it is. You're just simply testing out, is this true or false, by simplifying both sides and finding out if it works. So that would be, meaning the left side is true to the left of 2. In between 2 and 8, we could pick anything else in there. Again, we could pick, to test, maybe 3. In between, you could pick 5, whatever. And to test 3, you're plugging that in. That'd be -2, absolute value of 5 minus 3. We want to know, is that less than or equal to -6? Again, plug it in and test it out. This one should turn out false. So we'll mark an F above that middle interval, knowing it's false. And then lastly, to the right of 8, we can test 9. And do the same thing where you plug in, so we have -2, absolute value of 5 minus 9, close absolute value. Is that less than or equal to -6? That's our question. Again, do a couple of steps of arithmetic. This one should turn out true as well. So we label above the right side interval true. Now remember, the whole point here is to end up with a graph and interval notation, but it's incredibly simplified at this point because all you do is graph where it's true. So that would be to the left of 2, with the boundary symbol according to the original, which in this case was an inclusive inequality. So it would be a bracket at 2 opening to the left, where the arrow is going to the left. Nothing in between 2 and 8, and then to the right of 8 also true, so we put a bracket and an arrow going to the right of 8. That's our graph. The interval notation could be written directly beneath. It's just summarizing the graph, so it's negative infinity with a parenthesis on it, comma 2 with a bracket. Remember, infinities always get parentheses, but the boundary of bracket remains. And then we union to hold that together with the other side, which would be a bracket with an 8, comma, positive infinity with a parenthesis. And that would be the interval notation and the graph summarizing for this solution.